time to build one. The growable array, the structure you reach for more than any other. A Python list, a JavaScript array, a Go slice, a C++ vector. Different names, identical guts. And by the end of this lesson, you'll have built those guts yourself. The build starts with the raw material, the fixed size array, one contiguous block of memory carved into equal slots. And that one choice, equal slots side by side, buys the array its superpower. Say each slot is 4 bytes, and the block starts at address 1000. Item 0 lives at 1000. Item 1, 1004. Item 7 sits 7 slots in, 28 bytes, 1028. The address of item I is just base plus I times the slot size. 1 multiply, 1 add, 1 load. No walking, no searching. Item 3 costs exactly the same as item 3 million. That's why indexing an array is order 1. It's not an optimization, it's arithmetic. Indexing is free because every element sits exactly where the formula says it must. Now watch that same rigidity send a bill. Take a million-element array and insert a new element at the front. Slot 0 is occupied, and there's no slot -1. So element 999,999 moves right, then the one before it, and the one before that. Every element shifts 1 slot over before you can write the new one. 1 insert, a million moves. Order in. Deleting from the front is the same story in reverse. Shift everything left to close the gap. And this isn't a textbook hypothetical. In Python, list.pop with no argument takes the last element, order 1. Pop of 0 takes the first and quietly shifts the entire list. Same method, one argument, a factor of a million in work. JavaScript's shift versus pop, identical trap. So the array's contract is now clear. The end is cheap. The front and the middle cost a shift. There's a harder problem than shifting. The block has a fixed size, and that size was a promise. You asked the memory allocator for 8 slots. It reserved exactly 8. And it was free to hand the very next bytes to someone else. So when element 9 arrives, the address where slot 9 would go may be the middle of another object. You can't just make the block longer, not reliably, which leaves exactly one move. Find a bigger block, somewhere else in memory. Copy all 8 elements across, free the old block, and then, finally, write element 9. That copy is order in. Every element, every single time you outgrow the block. So the question that defines this whole lesson is, how big should the new block be? Get that answer wrong, and the array you use every day would be unusably slow. Get it right, and the copying almost disappears. Here's the machine, and it's 3 words long. A pointer, to the block, a length, how many slots are filled, and a capacity, how many slots exist. Length and capacity are different numbers, and the gap between them is the entire trick. Deliberately allocate more than you need, so most appends land in spare room. When an append arrives, the structure asks one question. Is length less than capacity? If yes, the append is trivial. Write the element into the next free slot. Bump the length. Done. 2 steps, order 1. And notice where that right lands, right next to the previous element, in a block you touched a moment ago. By last lesson's rules, that cache line is still warm. The fast path is cheap on paper and cheap on the machine. So appends just stream into the block, one after another, until the spare room runs out, until length equals capacity. That's the moment the whole design pivots on. Length equals capacity, and an append arrives. Now the slow path. Allocate a new block, twice the old capacity. Copy every element across. Free the old block, then append like normal. Let's run it, starting from capacity 1, appending 9 elements. Append 1, fits. Append 2, full. Grow to 2, copy 1 element. Append 3, full again. Grow to 4, copy 2. Append 4, fits. Append 5, grow to 8, copy 4. 6, 7, 8, all cheap. Append 9, grow to 16, copy 8. There it is. Most appends were 2 steps, but appends 2, 3, 5, and 9 each triggered a full copy of everything so far, and append 9 alone cost 8 copies plus the write. That is the exact moment an innocent-looking append quietly costs order n. Same function call from the outside, wildly different bill. So what's the total damage? The first lesson already did this math, so let's just collect it. Appending n elements triggers copies at every doubling, 1 plus 2 plus 4, and so on, and that sum never reaches 2n. Spread the total across the n appends, and each one carries about 3 steps, constant. Order 1, amortized. The bank account from Lesson 1, every cheap append deposits a couple of spare tokens, the rare doubling withdraws the balance, and the account never overdrafts. But hold on to the fine print, because it matters more here than anywhere else in the course. Amortized means the average over a run is constant. It does not mean every append is fast. On a list of 100 million elements, some single append will stall while 100 million elements move. The sum is guaranteed, the spike is real. Both of those are true at once, and good engineers plan around both. Why double specifically? Well, the growth has to be a multiplier. Grow by a fixed step, say 10 slots, and a million-element array gets recopied every 10 appends. Quadratic in disguise, the GTA bug in a new costume. But the multiplier doesn't have to be 2, and real implementations disagree. Doubling means fewer copies, but right after a growth, the block is half empty. A 2 GB array could be squatting on 4. So, C++ vectors double in the GNU and LLVM libraries. But Microsoft's grows by 1.5x. Java's ArrayList, 1.5. Go slices double while they're small, then taper toward 1.25 as they get big. And Python lists barely overallocate at all, about an eighth extra. Every one of those teams did the same arithmetic and picked a different point on the same curve. More spare room, fewer copies. Less spare room, less waste. There is no free answer, only the trade. Now the marquee example, because this machine has a sharp edge, and Go engineers cut themselves on it weekly. A Go slice is the 3-word machine: pointer, length, capacity. And the crucial fact, slicing does not copy. Start with A, 4 elements, 10, 20, 30, 40. Take B equals A, sliced from 0 to 2. That builds a new header over the same block, length 2, but capacity 4, because the block runs past B's end. Now append 99 to B. The machine checks. Spare capacity? Yes. So it writes into the next slot of the shared block, which is A's slot 2. Print A. 10, 20, 99, 40. You appended to B and mutated A. Now append 3 more elements to B. This time capacity runs out, so append allocates a fresh block and copies. From that moment, B is divorced from A. Writes to one no longer touch the other. Same function, append. Sometimes it aliases, sometimes it divorces, and which one you get depends on a capacity you probably never checked. That Go story generalizes, so let's name the footguns. 1. Invalidation. When the array grows, every element moves to a new address, and the old block is freed. In C++, any pointer or iterator you saved into a vector is now pointing at freed memory. Using it is undefined behavior, a crash on a good day. In Go, an old slice header leaves you staring at the abandoned block while new appends land somewhere else. 2. The spike. Order 1 amortized still means some single append stalls for a full copy. Inside a game frame with 16 milliseconds of budget, or on the hot path of a trading system, that one spike is the incident. 3. The silent squat. Popping elements does not give memory back. A vector that once held 10 million elements and now holds 10 still owns the 10 million slot block in most implementations until you explicitly ask. Growth is automatic. Shrinking almost never is. And all three footguns share one antidote. If you know how many elements are coming, say so. Every language has the verb. C++, reserve. Go, make with a length of 0 and a capacity of n. Java, pass the size to the constructor. One allocation, up front, and every append for the rest of the loop is the two-step fast path. No copies, no spikes, no invalidation mid-loop, no half-empty block. Look back at the code from the first lesson, the duplicate checker. The Go version passed a size hint to make. The C++ version called reserve before the loop. That wasn't decoration, that was this lesson applied early. So here's the pattern to internalize. The growth machinery is a brilliant default for when you can't predict n. The moment you can predict it, pre-size, and the whole grow and copy drama simply never happens. Step back and look at what you've built. A pointer, a length, a capacity, and a grow rule. That's a Python list. That's a JavaScript array. A Go slice, a Java ArrayList, a Rust vec, a C++ vector. The default collection of every mainstream language is this machine. Fixed block underneath, doubling trick on top. And you now know its fast path, its slow path, and its sharp edges. Two doors we walked past, deliberately. The grow and copy move comes back in lesson 12, when hash tables resize themselves with the same trick. And the linked list, the structure that never copies on growth, gets its honest hearing in lesson 5. Next up, though, a structure that looks exactly like an array of characters and refuses to behave like one. You cannot change a string, not one character, not in Python, not in Java, not in Go. Why every language made that choice, what it buys you, and the hidden order n that turns an innocent loop of concatenations into a quadratic accident. That's next.